Hello. Imagine you're buying something on a banking application, let's say for 2000 rupees. You click on the button pay and then you see a spinner. A couple of seconds later, you see a timeout. Now, you're not sure if the payment went through. So, you decide to click on the pay once again. Now, sometime later, you see that you were charged twice. You see two notifications of 2000 rupees being charged. So, what actually happened? But more importantly, how does a real world payment system make retries safe? The answer lies in a concept called idempotency. But idempotency is not enough. We also need database constraints, we need payment states, and we need to also make the event and webhooks idempotent. So let's break it down. Let's start with a simple payment flow. The customer taps pay button in the application. The app sends a request to our payment service. The request contains things like order ID, amount, currency, and payment details. Our payment service validates the request, parses the request in the payment database, and sends it to our payment provider. The provider processes the payment and returns the result. Our service then returns the result back to the application. If every request and every response arrive exactly as expected, the flow looks simple. But distributed systems rarely behave that perfectly. There are several ways duplicate requests can happen. The customer may double tap the pay button. The mobile application may automatically retry. An API gateway or backend service may retry after a timeout, or the payment provider may successfully process the payment, but the response may get lost somewhere on the network. The last case is actually important. A timeout does not mean the payment failed, it only means we did not receive the answer. The original request may never have reached the provider, or the provider may already have succeeded and only the response was lost. Now, imagine a naive payment API. Every time it receives a post API request with URI, API weave-in payments, it creates a new request and sends a new request to the payment provider. The first request reaches the provider. Customer is actually successfully charged. But let's say the response is lost. The application sees a timeout and retries. Our server treats that retry as a brand new payment. So it creates another payment record and sends another charge request. Now we may have two payment records and two charges for the same customer. Disabling the pay button helps with accidental double clicks, but it does not prevent us from network retries, server crashes, concurrent requests, or duplicate messages. The prevention has to exist on the server. This is where idempotency key comes in. For each logical payment attempt, the client generates a unique identifier. In real-world applications, it's usually a UUID. But for simplicity, let's take an example that it is payment attempt 123. The first payment request sends this key to our payment service. If the request times out and the client retries, it sends the same idempotency key again. When the payment service receives the request, it checks whether it has already seen that key. If the key is new, the service reserves it and begins processing the payment. If the payment has already succeeded, the service does not create another charge. Instead, it returns the previously stored result. If the payment is still being processed, the service can return an in-progress response and ask the client to check again later. So now, Multiple HTTP requests can represent a single logical payment. That is the core idea behind idempotency. Now, who generates this idempotency key? It is usually the request originator who generates the key. In this case, it is client. There is one important rule here. The same idempotency key should always represent the same logical operation. Imagine the first request says amount 2000 rupees, and then the retry uses the same key but changes the amount to 3000 rupees. The server should reject that request. Otherwise, a client bug could accidentally connect two different payments to the same idempotency record. So, in practice, systems often store both the key and enough request information to verify that a retry is actually the same operation. However, simply checking whether the key exists is still not enough. Suppose two identical requests arrive at almost exactly the same time, and suppose they are handled by two different instances of our payment service. Service A checks the database, the key does not exist. At the exactly same time, Service B checks the database, the key also does not exist. Now, both services try to create the payment. This is a race condition. To prevent it, idempotency key should have a unique constraint in the database. Only one request can successfully insert that key. The other request receives a duplicate key error. It reads the payment created by the winning request and returns the same payment state. So, the database becomes the final protection against concurrent duplicate request. The payment record moves through a predefined workflow through explicit states. For example, when we receive an API request, the payment record's state is received. Then it gets updated to processing when the external payment provider is called. And finally, gets updated to succeeded or failed. Imagine our payment service sends a charge request to the payment provider. The provider successfully processes the payment, but before our service record succeeded, the service crashes, or the success response is lost. Now there's a discrepancy. Our database says processing, but the provider says succeeded. So what should we do? Can we simply send the payment request again? No, not safely. Because the provider may already have charged the customer. This is why idempotency should continue across system boundaries. Our service should send a stable idempotency key or merchant reference to the payment provider as well. If we retry using the same reference, the payment provider can recognize that it has already processed the operation and return the existing result instead of charging the customer again. Well, sometimes even that is not enough. The payment may remain uncertain for a while. In that case, our system can query the provider using the payment reference ID, or it can wait for an asynchronous status update via the webhook. And later, a reconciliation process can compare our internal payment record with the provider's record and repair any mismatch. The most important principle being idempotency should not stop at our own API boundary. Every place where a retry can happen needs its own strategy. Payments also involve asynchronous events. For example, provider may send us a webhook saying that payment succeeded. But what if our webhook endpoint receives the event, processes it, and then fails before sending the acknowledgement, the provider may send the same webhook again. Message queues can behave in a similar way. A message may be processed successfully but delivered again if the acknowledgement is lost. So, webhook and event consumers also need to be idempotent. A common approach is to use provider's event ID. We store that event ID with a unique constraint. The first time we see it, we process the event. If the same event appears again, we simply acknowledge it without repeating the business action. So, how does a real world payment application prevent double charge? First, use idempotency key, which will be unique. Second, store that key with a unique constraint in our database. Third, use states to track our payments like received, processing, success, and failed. Fourth, propagate a stable reference ID to the downstream payment provider. And lastly, deduplicate events and webhooks before processing a business logic. The core principle is simple. For each retry boundary, we need to have an idempotency strategy. Thank you for watching.